Now, this one's the most fun because, well, partly because it introduces some fun new notation, which will turn up more when we do inequalities at the end of the year. But yeah, are my eyes playing with me? Is that really just an upside down A? And the answer is yes, it is just an upside down A. What does it mean? What does it mean? It's shorthand for all values of. Okay, so I read that as if two polynomials of degree n are equal for more than n values of x, then they're equal for all values of x. They are the same polynomial. Okay, now, what does this mean? If we've got two polynomials, call them a of x and b of x, okay, and if we know, for instance, that they are of degree, I don't know, 5, okay, just as an example. Okay, if there are 6 instances where the two polynomials are the same, for instance, I find out that a of 1 and b of 1 are the same, okay, and a of, I don't know, minus 10 and b of minus 10 are the same, and so on. And if I can get 6 of these, okay, if I can find 6 points where they actually line up, then I can know for certain that they'll line up for all values that I can come up with. Okay? Or if it was not degree 5, if it was degree 50, if I can find 51 values where they're the same, or you get the idea. Okay? Now, why is that? Well, how can we see that it's true? Okay, now like with the previous ones, I'm going to try and draw it and see if that's enough of an explanation. Okay. People often get hung up on the language of this property because it's kind of obtuse and vague. But if you put it in terms of graphs, it's really easy. Let's think about two polynomials of degree 1. Okay, so if I've got a of x and b of x having degree 1, that means they're straight lines, right? So suppose they've got they're equal for, let's say, one value of x. Okay. Now I'm now going to think of a and b in terms of what their graphs might look like. Okay. So if I know a and b are equal, say, suppose a naught and b naught are the same. Suppose they're both equal 5. Okay. Now that means there's this point 0, 5 that both polynomials pass through. Okay. But if all I've got is one value, right, this might be a, okay, and I can have a whole bunch of b's that all go through that point. In fact, an infinite number of them, okay? But if I know that both a and b go through 2 points, right, so this is now the more than n values, okay? If you put in 2 points, like say here and here, right? So a might go through there. There's only one other, well, not other even, there's only one polynomial that'll fit through both of those points, okay? You can't draw like another one and he's kind of like, yeah, I'm gonna, yeah, and come back, okay? Unless, of course, their degrees don't match, right? In which case you've got a completely different scenario. And you can generalize this up, right? Suppose we did a quadratic, okay? You go ahead and try it. Pick for yourself 3 points, okay? Say 1, 2, 3, okay? And draw a parabola that passes through all of the points, okay? Like, I don't know, I missed. I'm gonna be creative. There we go, okay. Now, if these are my 3 points, okay, there is no other parabola that you can draw that will fit all 3 of those points, okay? Because I've got degree 2, and I've got more than 2 points where these two polynomials apparently agree, okay? So that means they must agree for every other single value that's there, okay? Does that make sense?